Welcome to A-Level and AP Physics. In today's lesson, we will discuss one very important past paper question on thermodynamics from March 2022, paper 4, variant 2. I said this question is very important because in this lesson, we will discuss some key concepts about thermodynamics, and these key concepts are very important for your exam. For question number 2, it is given to us a fixed mass of an ideal gas has a volume V and a pressure P. The gas undergoes a cycle of changes from X to Y, Y to Z, and finally Z to X, as shown in figure 2.1, as shown on this PV diagram. Question is asking us, for part A, we need to state the change in internal energy delta U for one complete cycle X, Y, Z, X. Means for the gas, if this is the complete cycle from X to Y, then from Y to Z, and finally from Z to X. If this is a complete cycle for a gas, we need to state what is the change in internal energy. Let's try to understand some key concepts about internal energy before we answer this question. So the first key concept you need to understand is delta U is equal to 0 if the initial and final state are the same. If initial and final state are the same. So simply we can say if initial and final states are the same. Initial and final states are the same for any ideal gas. In that case, delta U is equal to 0. Or simply we can say for any complete cycle. For any complete cycle. Means if gas undergoes a cycle of changes. So we can say for any complete cycle, delta U is equal to 0. So very important point. Actually, this point you need to answer this question. And the second thing we need to understand is that we can also say delta U is independent of path. It doesn't matter if gas started from here, for example, from X, it goes this way, then go this way, then go this way, and finally come to this one. Still, delta U is equal to 0 if initial and final states are the same. So in this case, you can see this gas undergoes a cycle of changes. That's the reason delta U has to be equal to 0. And this is B mark. If you have written this one, you will get this 1 mark. For part B, question is asking us to calculate amount N of gas. Means question is simply asking us to calculate value of N. Means the number of moles. And we are talking about ideal gas in this case. For any ideal gas, PV is equal to nRT for any value of P, for any value of V, and for any value of T. So simply in this case, we need to calculate N, we need to calculate number of moles. So simply we can rearrange N is equal to PV over RT. For this ideal gas, value of P is given to us. So this is value of P. So simply we can plug in values now. We can say P is equal to 1.5 times 10 to 5, and we need to multiply this one with V, and the value of V is given to us, and this is equal to 4.2 times 10 to negative 3, and we need to divide by gas constant, and value of gas constant is 8.31 joules per mole per Kelvin. So we can plug in this value here, and finally temperature has to be in Kelvin. Temperature is already given in kelvins, so simply we can plug in value of temperature. So if we calculate this one, our final answer will be 0.14 moles up to 2 SF. So this is our final answer up to 2 SF. We have to use 2 SF in this case because the least number of SF we have is 2, and here also we have 2. So our answer has to be up to 2 SF. And this is our final answer. This question has only 2 marks. If you have used this formula, you will get 1 mark. And if you have got the right answer, you will also get a second mark. Means you will get 2 marks in total. So this is how we can answer this type of problems. For part C, we need to complete table 2.1. Means we have to enter the missing values of P and missing values of V in this table. So these missing values we have to enter. In order to answer this question, we need to understand two things. First thing, we need to understand how to use PV is equal to nRT, this ideal gas equation. And the second one, we need to understand how to read PV diagram. So this is the first thing you need to understand. The second one, you need to understand how to read PV diagram. If we look at X and Y, so the value of P at this point and value of P at this point is the same. So simply we can say the value of P for state X is the same as value of P for state Y. And that value is given here. That is equal to 1.5. So simply we can say this is equal to 1.5 times 10 to 5 Pascal. So here we can enter for Y. This is also 1.5. So this is how you can find the value of P at Y. Now let's try to find out value of V at Y at state Y. So simply we can say this is Vy and we need to find out value of V at Y. For that purpose we have to use this ideal gas equation. We can say in this case V is equal to nRT divided by P. And we have already calculated that was equal to 0.14 moles and R is gas constant, so we can say this is 8.31 joules per mole per Kelvin and temperature is in Kelvin. T has to be in Kelvin. It is already given, it is in Kelvin, so we can write down value of T. Now we need to divide by value of P and the P at Y we have that is 1.5 times 10 to 5. Now if we solve this one, our final answer will be 1.8 times 10 to negative 3 cubic meters. And that is the answer for V. So simply we will write down V is equal to 1.8 cubic meters. 1.8 times 10 to negative 3 cubic meters because 10 to negative 3 is written here. So you no need to write down here. Now we need to find out value of V at Z. If you look at this one, from Y to Z, there is no change in volume. So volume stays constant, but P is increasing. So simply we can say Vy is equal to Vz. We can read this one simply from diagram. So value of V at Z is also equal to 1.8 times 10 to negative 3. And that is the answer. This question has 2 marks. If you have got right value of the P, you will get 1 mark and this is the mark. And if you have got these 2 values right, you will get the second P mark. So this is second P mark. For D, it is given to us the first law of thermodynamics for a system may be represented by the equation. Delta U is equal to Q plus W. We need to state with reference to the system what is meant by these symbols. First one is delta U. Delta U simply is the change in internal energy of the system. So we can say this is change in internal energy of the system. So this is how you can write this. Change in internal energy of the system. So this is one thing you can write down. Even you can say increase in internal energy of the system. It can be positive or negative. Q. Next one is the Q. Q is heat supplied to the system. Better way to say this one is thermal energy supplied to the system. So this is how you can write down. Thermal energy supplied to the system. So you have to write down system here. Next one is W. W is the work done on the system. So W is work done on the system. Often we say work done on the gas. So gas is our system. Work done on the system. So this is what you need to write down for part 1. If you have written this for delta U, you will get 1 mark and this is B 1 mark. And for Q, you will also get 1 B mark. And for W, this is also another B mark. If you have written these 3, you will get 3 B marks. For the second part, question is asking us to explain how the first law of thermodynamics applies to the change Z to X. Means from this state to this state. Z to X. Z to X. But if you look at Z and if you look at X, simply we can see that the volume is increasing from Z to X. So the gas is expanding. So this is expansion. We can also find out from this table, if we go from Z to X, so this is the value of P actually, but if you look at value of V, so you can see from Z to X, V is increasing. So we can write down V is increasing. So this is expansion process. If it is expansion, it means work is done by the system, or we can say work is done by gas, and work done by gas is taken as negative. So this is one thing we can get from this PV diagram. Now let's look at temperature now. If we go from Z to X, you can see the temperature is decreasing. So if temperature decrease, it means delta U is negative, means the change in internal energy, this is negative. So this is negative because delta U, this is equal to 3 by 2 K times delta T. If the change in delta T is negative, it means delta U is negative. Now if we write down the first law of thermodynamics, we can say Q plus W, this is equal to delta U. As the change in delta U, this change is negative, and W, this is also negative. But for the Q, it can be positive, it can be negative. It depends on the exact value of Q, means how much Q has been added. So it can be positive, means heat can be supplied to the system, or heat can be released from the system. It depends on the exact values of W and exact value of delta U. But we don't have the exact values of delta U, and also we don't have exact value of W. So we cannot say something about Q. So simply we can mention these 2 points. So we can say as volume increases, work is done by gas. As temperature decreases, it means internal energy decreases because the change in internal energy is negative. So you have to write on these 2 points. You will get 2 marks. But don't try to explain this one with the help of thermal energy, because that is not possible, because we don't have the exact values of W and we don't have the exact value of delta U. This is how you can write down your final answer. If you have mentioned these 2 points, you will get 2 marks. As volume increases, work is done by gas. So this will be 1 mark. You will get 1 B mark for this one. And the second B mark is if you have written temperature decreases, so internal energy decreases, you will get second B mark. Welcome to A-Level and AP Physics. In today's lesson, we will discuss a typical type of question on electric field from March 2022, Paper 4, Variant 2. In this question, we will discuss what is represented by electric field lines. Then we will discuss how to find, means how to calculate potential at any point between 2 opposite charges. Mean in the region between 2 opposite charges, how we can calculate value of potential. Then we will discuss about electric field between 2 opposite charges. We will also sketch a graph of potential versus distance. And at the end of the video, we will also talk about what is direction of force on an electron if it is placed at equal distance from 2 opposite charges. So we're going to discuss some very important points about this chapter in today's lesson. So listen carefully. First of all, try to do question by yourself and then look at the solution. For part A, we need to state what is represented by electric field line. Let's try to understand this one with the help of positive charge, means the electric field around a positive charge, and electric field around negative charge. So let's say we have negative charge here. So here we have negative charge, and this is the electric field around this negative charge. They have the equal amount of charge. So that's the reason we simply draw 4 for electric field line. This also tells us that they have the equal amount of charge because they have equal number of electric field lines. Now, if I need to draw direction of electric field lines here, for positive charges, we draw pointing away from positive charge. So we draw arrows like this, pointing away from positive charge. But for negative charge, we will draw pointing towards negative charge. We draw arrows like this. This is what question is asking you. Why we draw these arrows like this? For positive charge, we need to understand why we draw away from positive charge. We follow one convention. Convention is that if we place a positive charge nearby any charge, so these lines tells us direction of force on positive charge. In this case, you can see this is a test charge. This is a small charge, so it does not affect the electric field of source charge. So this big charge we call this is source charge. Test charge is very small. Test charge. So the force on this charge, you will see it is pointing to the right. So that's the reason we draw these lines pointing away from positive charge. If we place test charge here, test charge has to be positive. So again, repulsive force between these two, and the force is pointing upwards. And same it is true if we place here, anywhere you place in the electric field, the force will be pointing away from positive charge. That's the reason when we draw these arrows, we draw pointing away. And same is true for the negative charge. But if I place again test charge here, test charge is always positive. If I place positive test charge here, the force on this positive test charge, this is to the left. So that's the reason we draw this arrow to the left. Now, if we place positive charge, test charge here, there will be attractive force between positive charge and this negative charge. So test charge will be attracted. So that's the reason we draw arrows pointing towards negative charge. So that's the thing you need to understand to answer this question. So simply electric field lines tells us direction of force on positive charge. In this case, direction of force on this positive charge is to the right, and here it is to the left. So this is what electric field lines are telling us. And that's all what we need to write down for this question. And so this is how you can write down your answer. So simply you can say electric field lines tells us direction of force. So you will get 1 mark, 1 B mark. And if you have mentioned on positive charge, you will get 2nd B mark. And there are 2 marks for this question. For part B, it is given to us there are 2 point charges P and Q, and charges are placed at a distance of 0.120 meter apart from each other, as shown in figure 4.1. Charge on P is positive charge and the magnitude of charge is 4.0 nanocoulombs, and charge on Q is negative and the magnitude is 7.2 nanocoulombs. For this question, we need to determine the distance from point P of the point on the line joining the 2 charges where electric potential is 0. Means we need to find a point at a certain distance from P where potential is 0. It means the value of V is equal to 0. Potential is equal to 0. Let's say that point is at a distance of x from P. We just assume a certain distance x, and then we will find the magnitude of x. Means the value of x we will find out. And let's say this distance, if this distance is x and the total is 0.120, so the distance between Q and that point will be 0.120 minus x. Now simply we need to find out what is value of x. Now, first of all, let's try to understand a little bit about potential. For positive charges, so I will write down for positive charges, the potential of positive charge is positive. For positive charges, potential is positive. So I will simply say potential is positive. Why potential is positive? Because K is equal to, V is equal to KQ over R. If Q is positive, it means V is also positive. Very important point. You need to enter signs. Very important point. For negative charges, we can also say for negative charges, potential is negative. So we can write down here. For negative charges, V is negative. Why V is negative? Because V is equal to KQ divided by R. If Q is negative, it means V is also negative. So simply we can say positive charges produce positive potential and negative charges produce negative potential. Or simply you can say potential of positive charges is positive and potential of negative charges is negative. Very important point. Now let's try to answer this question. It is given to us that we need to find the point where potential is zero due to these two charges. So first we write down the potential of P. So we will say the potential of P plus potential is a scalar quantity. So Vp plus Vq has to be equal to 0. Now Vp we can find out, mean the potential due to positive charge, that is Kq. I will simply say K times Q. Q in this case is 4 nanocoulombs. So this is 4 times 10 to negative 9 coulombs divided by distance. Distance is equal to x. Distance is equal to x. So this is plus sign. So let me clean this one and rewrite. So this is plus sign here. And this is negative charge. So the potential of this one will be negative. So we will use negative sign here. So this is negative 7.2 times 10 to negative 9. And this is divided by the distance. And the distance from this point, I mean the distance between charge and the point is 0.120 minus x. Now from here, the first thing, there are few things we can cancel out. The first thing we can cancel is the k. I'm just using k here, but k you need to understand k is equal to 1 over 4 pi epsilon naught. You can also enter 1 over 4 pi epsilon naught. To keep it just simple, I'm using k. So we can cancel k with k. And the power 10 to negative 9, we can cancel with 10 to negative 9. Now we can simplify this. If we simplify, we're left with 4 divided by x here. And this is negative here. So on other side, this will be positive. So this will be equal to 7.2 divided by 0.120 minus x. Now, if we cross multiply, it means we multiply like this. Cross multiply. If we cross multiply, in this case, we will get 4 times 0.120 minus x. This is equal to 7.2 times x. And from here, we can find out, means the value of x will be 0.043 meters. And this is our final answer. Our final answer has 2 SF. Because the least number of SF in data, we have 2. So we are using 2 SF here. So this is our final answer. This question has 2 marks, and the first mark you will get if you have written Vp plus Vq is equal to 0. Means you have entered value here. So this mark will be C1 mark. And the second mark is the answer mark if you have got the right answer. So this one is answer mark. For our second part, we need to state and explain without calculations. Means we don't need to do any calculations for this part. Whether the electric field is 0 at the same point at which the electric potential is 0. This question is a bit tricky one. This is testing your understanding of electric field and potential and the relationship between electric field and potential. So first of all, let's try to understand what is the relationship between electric field and potential. Electric field is equal to negative of potential gradient. So simply we can say this is equal to negative delta V over delta R. Now this is the distance. So electric field is the negative of potential gradient. So electric field is 0 if the gradient of V against R graph is equal to 0. Means E is 0 if the gradient of this one, means delta V over delta R, this is 0. So simply we can say if the gradient of V against R graph is equal to 0. If the gradient of this one is 0, it means that electric field is equal to 0. If the gradient of V against R graph is equal to 0, it means electric field is 0. Now, let's try to sketch, first of all, electric potential against R. First of all, we will sketch potential against R graph. So, V against R. In this case, we have 2 charges. 2 charges, one charge is positive and one is negative. So, I will place the positive charge here, means this positive charge. So, it is placed here. And I will place, let's say, the negative charge, it is placed here. So, this one is the negative. So simply let me draw here. This one is the negative charge. This one is negative charge. So this is negative. Positive charge. Its potential is positive. So potential V is equal to KQ over R. mean r is the distance from the charge. So as the distance from the charge is increasing, the potential of this one will decrease. Now if you look at the negative charge, now the potential of negative charge, this is negative, so it will have certain value, but this value has to be greater because its charge is greater, so its potential will also decrease with distance. But we will see at certain point the potential due to these two charges, we will get graph like this. I mean, if we combine the potential of these two, at this point you will see the potential due to these two charges is zero. But if you look at the gradient of this one, gradient is not zero. So it means at this point potential is zero, but electric field is not zero because the gradient is not zero. So electric field, we will say, at this point is not equal to zero because electric field is equal to negative delta V over delta R, and this is not equal to zero, means the gradient is not zero, but V at this point, this is equal to zero. And that's the point you need to understand to answer this question. So potential can be zero, but at that point electric field cannot be zero. Now let's try to answer this question based on electric field concept. So we will look at that certain point again, and at that certain point we have discussed potential is equal to zero. Now we will look at this point again, and we will find out electric field due to positive charge at this point, and we will find direction of electric field due to negative charge at this point. If you look at direction of electric field at this point due to positive charge, so this will be pointing to the right. So we will say this is direction of electric field due to positive charge. Now if you look at electric field at this point due to negative charge, we will write down this is also to the right because electric field lines are pointed towards negative charges. So electric field due to Q is also to the right, and due to P is also to the right. So it means the net electric field at this point is the sum of these two fields. So the net electric field will be somewhat like this. So this is our net electric field. Electric field is a vector. So this is our net electric field. Means the sum of vector sum of these two fields. This is not equal to zero. So simply we can say in this case net electric field is not equal to zero because fields due to P and Q, they are in the same direction. So that's reason E net is not equal to zero. Even potential at this point is equal to zero. And that's all what we need to write down for this question. So this is how you can write down your answer. And in this answer, this is your statement. So you have to write down this one in your answer because question is asking you to state and explain. So this is your statement and this one is explanation. So if you have stated and you have explained, you will get 2 marks. Actually, for this question, we have 1 mark. In order to get this 1 mark, you should have the statement in your answer, meaning you have mentioned no, and you have explained why it is not 0. So you will get 1 mark, and this is B mark. For third part, it is given to us an electron is placed at point X, and it is at equal distance from both P and Q as shown in figure 4.2. Means electron is simply placed at this point, and it is at equal distance, means the distance between electron and P and the distance between Q and electron, they are the same. But the charge on P is plus 4.0 nanocoulomb, means it has positive charge. But Q has negative charge, and this is equal to 7.2 nanocoulomb. As distance is the same, but charge is different, so the force on electron due to Q and due to P will be different. But force due to Q will be greater, so we will draw 1 arrow here. Because these two charges, they have the same charge, it means there will be repulsive force on electron. So this is force on electron due to negative charge Q. And the force due to charge P, this will be attractive because these two are opposite charges. So the force will be in this direction. So this is attractive force. I draw this arrow shorter because force due to P is weaker than force due to Q. So this is simply, we have these two forces, these are acting on this electron. We simply need to sketch actually, so it doesn't matter. The length of arrows is not very important. To just give you idea how we will draw the resultant force on this one, I have drawn one arrow this is longer because this force is greater and this force is weaker. Now simply we need to add these two forces. So we will use parallelogram method. So I will take this vector from here. I will just draw here. So I will be using dotted lines. So this is direction of force. Now we will take this vector and we will place here. And now we need to find the resultant of these two vectors. So the resultant is from the tail of these two vectors to the head of these two vectors. So simply tail to head. So we will join this one here. And this is direction of resultant force, and you can see this resulting force is below horizontal, and that's all what we need to do. Simply you need to draw this arrow. So this one is the resultant force on electron, but if these two charges they were equal in magnitude, then the resultant force will be along horizontal, but in this case it has to be below horizontal because repulsive force is greater than attractive force. So this is how you can draw the resultant force. Welcome to A-Level and AP Physics. In today's lesson, we will discuss an important past paper question on capacitance from March 2022, paper 4, variant 2. This question is based on new specifications and very important for our coming exam. For question number 5, the variation with potential difference V of the charge Q on one of the plates of a capacitor is shown in figure 5.1. As you can see here, we have charge Q on y-axis and potential difference across plates is on x-axis. It is also given to us the capacitor is connected to 8-volt power supply and two resistors R and S as shown in figure 5.2. So in this case you can see capacitor is connected here. This is symbol for capacitor and this is symbol for power supply. This is 8 volts power supply. Resistor R is connected here at this point and resistor S is connected here. And this is our switch, two-way switch. This switch can be moved to X, this can also be moved to Y. When this switch is at position X, this capacitor is charging. Very important point, we need to understand when the capacitor is charging and when the capacitor is discharging. In this case, capacitor is charging because there is power supply in this loop, or simply you can say in this circuit. But if we move this switch to Y, this capacitor will start discharging because in this loop there is no any power supply. There is only resistor. So capacitor is at higher potential, it will start discharging. So very important point we need to understand about charging and discharging. Now let's move on to part A and try to answer part A. For part A, question is asking us the switch is in position X so that the capacitor is fully charged. We need to calculate energy E stored in the capacitor. In E energy stored in the capacitor we need to calculate. So energy stored in a capacitor is equal to 1/2 QV, or we can say this is 1/2 CV square. Our energy stored in a capacitor is 1/2 Q square over C. But if you look at this graph, in this case we have value of V and we have value of Q. So simply we can use E is equal to 1/2 QV and we can find out energy stored in the capacitor. Now let's try to understand what value of Q we have to use and what value of V we have to use to calculate energy stored in the capacitor. So the first thing we need to understand is the voltage of the battery, means the voltage of this battery is equal to 8 volt. So when this capacitor is fully charged, means when there is no current flowing in this circuit, at that time the potential difference across the battery and the potential difference across the capacitor, these two potential difference they will be same. So this is capacitor. So the potential difference across the capacitor, when this is equal to potential difference across terminals of the battery, current flowing will stop. So in this case, battery voltage is 8 volts. So the capacitor voltage also will be 8 volt when this is fully charged. So this is the key concept you need to understand. In this graph, you can see this is the 8 and this is the value of potential difference across capacitor when this is fully charged. So we have value of V and the value of Q is 1.2. So simply you can say you just need to calculate area under this line. So now we can plug in values. We have 1/2 and value of Q is 1.2 times 10 to negative 4 and we need to multiply with value of V, that is 8 volts. So our final answer in this case will be 4.8 times 10 to negative 4 joules up to 2SF. So this is our final answer for E. This question has 2 marks. You will get first mark if you have used this formula or you have written area under graph. You will get C mark. And the final mark is the answer mark. If you have got right answer, you will get answer mark. So the tricky point, this is the most important point. You need to understand when the capacitor is fully charged, the potential difference across the capacitor can be equal to the potential difference across terminals of power supply. Terminals of power supply. So very important. For part B, it is given to us the switch is now moved to position Y. Means when capacitor is fully charged, we move this switch to position Y. When we move to position Y, this capacitor will start discharging. So simply we can write down now capacitor is discharging. And question is asking us, we need to show that the time constant of the discharge circuit is 3.3 seconds. So how we can calculate time constant? Time constant, we use letter tau for time constant tau, and this is equal to RC. And this R actually is very important. This is resistance of discharging circuit. The resistance of, we can say this is resistance of discharging circuit. Also you can say discharge circuit. Resistance of discharge circuit. Very important point. So in this case, the discharge circuit has a resistance equal to 220 kilo ohms. So simply we can use here R is equal to 220 kilo ohms. So this is value of R. Now we need to calculate value of C as well. But Q is equal to CV. Simply we can say C is equal to Q over V. C is equal to the charge on one plate of the capacitor divided by potential difference between the plates. So when the charge on one plate of the capacitor is this one, the potential difference across two plates, that is equal to 8 volts. So we can say in this case the capacitance, this will be equal to 1.2 times 10 to negative 4 divided by 8. So this one is capacitance 8.0. Now simply we can plug in value of C and we can calculate tau. So value of C is 1.2 times 10 to negative 4 divided by 8.0. So our final answer in this case is 3.3 seconds up to 2SF. Because this data has 2SF, this also has 2SF. So least number of SF we have 2. So we can say 2SF. And this is our final answer. This question has 2 marks. The first mark you will get if you have used this formula. And the second mark you will get if you have got the right answer. For the second part, it is given to us the fully charged capacitor in A stores energy E. We need to determine the time taken for the stored energy to decrease from E to E by 9. So this question is simply about the relationship between energy and time. But we don't have any direct formula or equation that link energy and time. But we have equations for discharging. We have V as a function of time, means we can find value of V at any given time, mean the potential difference across plates of capacitor by using this formula. And this is the V max, maximum value of potential difference, times E to the power of T over RC. And this is the time constant. We can also use Q as a function of time. This is equal to Q initial value or Q max, we can say, times E to the power of T over RC. And T is the time taken. We also have relationship for I as a function of time. This is also equal to I naught, maximum value of I, times e to the power of negative t over RC. We can use them and we can find the value of time. But if we have value of t, then energy means if we have value of V, when energy becomes E by 9. So first of all, we need to find out value of V. Or we can find value of Q, or we can find value of Y. But in this case, it is easy to find value of V. So we will just focus on V. So we will find out value of V when energy stored in the capacitor is E by 9. So let's start to find out value of V. So we will start from here. Energy stored in a capacitor, let's say this is E naught, this will be equal to 1 half C V naught square. But in this case, we can write down E naught over V naught square. This will be equal to 1 half C. The capacitance of capacitor is constant. So simply we can say this will be equal to some constant. We can say that E naught over V naught square, means the ratio between these two quantities will stay constant. So let's say we have the new energy stored, that is E new. We have to find out what is new value of V. Now from here we can find out value of V. E new, as it is given to us, E new is equal to E naught by 9. So we'll write down here E new is equal to E naught by 9. From here we can rearrange, we can write down V new. This will be equal to E new times V naught square divided by E naught. E new is E naught by 9. So this is value of E new. And we have V naught square. And this is divided by E naught. Now from here, you can see we can cancel E with E. So E we can cancel with E. So we left with V naught square divided by 9. Or simply we can say V new, if we take square root on both sides, we will get this is V naught by 3. And that is the value of V new. And now we can use value of V new and we can use this equation and we can find out value of T. Now let's try to find out value of T using the formula V as a function of time. This is equal to V max times e to the power of T over RC. Or we can simply say this is equal to V naught e to the power of negative T over tau. And tau is time constant. Value of tau we have already calculated, so we can plug in value of tau. Tau is 3.3 seconds. Now value of V new, we can rewrite this formula. So V new, this is equal to V naught e to the power of T over tau. V new we have calculated, this is V naught by 3 and this is equal to V naught e to the power of negative T over 3.3. So V naught we can cancel. We simply left with 1 over 3. This is equal to e to the power of negative T over 3.3. If we take natural log on both sides, we can say this is 3 to the power of negative 1 e to the power of negative T over 3.3. Now if we simplify this log, we can say this is negative come in front of log. So this is ln of 3. This is equal to negative T over 3.3 because ln of E is 1. So let me write on here. Ln of E, this is equal to 1. So this negative we can cancel with negative. So T from here is simply equal to ln of 3 multiplied with tau. And our final answer in this case will be 3.6 seconds up to 2 SI. So if you have done this working, you will get 4 marks for this question. The first mark is if you have used the relationship E is equal to 1 half C V square. You will get 1 mark. So this is 1 mark and this is C 1 mark. And the second mark you will get if you have got the relationship that V new, this is equal to V naught by 3. So this is an other C mark you will get. And the third C mark you will get if you have used this formula. So if you have used this one, you will get the third C mark. And the fourth mark you will get if you have got the right answer. So this is how you will get these 4 marks. And this question is very important because this is based on new syllabus. Maybe you will see this question in May-June exam as well. Maybe they ask you in a little bit different way, but this concept maybe will appear in coming exam. So try to understand this one and try to master this concept. For part C, it is given to us a second identical capacitor is connected in parallel with the first capacitor. So it simply means that there is another capacitor that is identical to the first one and is connected in parallel with first capacitor. So this is how new capacitor is connected. And question is asking us, state and explain the change, if any, to the time constant of the discharge circuit. So the first thing we need to understand is, now in this case, when the capacitors are connected in parallel, and if two capacitors, they are identical, so it simply means that the capacitance is simply double. So you can also imagine like that. If we combine these two plates, you see area of the plates increase, but the distance between plates is the same. So it simply means that capacitance is double because capacitors are connected in parallel. So we can say capacitance is double. So this is the first point we need to understand. Now the second thing we need to explain is time means the tau. Tau is equal to RC. If the C is double, so it means tau is also double because resistance of discharge circuit remains constant. So it means tau is also double. So that's all what we need to write on. 2 points, and this question has 2 marks. Let me show you the answer. This is how you can write down the answer. First mark is M mark. Means you must get this mark to get the second mark. So if you have written capacitance is double, you will get 1 mark, and that is a M mark. And the second mark you will get if you have written time constant is also double. If you simply write down time constant is double, but you haven't written first point, you will get no mark. So you have to write down, first of all, capacitance is doubled, then you can say time constant is doubled because capacitance is doubled. Welcome to A-Level and AP Physics. In today's lesson, we will discuss one very important past paper question on electromagnetic induction from March 2022, paper 4, variant 2. I said this question is very important because this question will challenge your understanding of magnetic flux and your conceptual understanding of magnetic flux linkage. So we will discuss these points in today's lesson. We will also talk about a typical question on Lenz's law, and at the end of this lesson we will also discuss about electromagnetic induction principle. For question number 6, it is given to us a smaller solenoid is placed inside a larger solenoid, but cross-sectional area and number of turns of smaller solenoid are given. And also we have cross-sectional area of larger solenoid and also the number of turns on larger solenoid. So these informations are given to us. It is also given to us that larger solenoid is connected with DC power supply. As it is connected with DC power supply, it means that magnetic field density, or simply you can say B, is uniform inside the solenoid, inside larger solenoid. So B is uniform and B is constant. So we can say B is uniform and B is constant. It is constant because it is not changing with time because current is constant. So B inside larger solenoid is uniform and constant. Now let's try to understand what is magnetic flux, because part A is asking us to compare the magnetic flux in the two solenoids. Magnetic flux simply equal to BA cosine of theta. Cosine of theta, and theta is the angle between B and A. Magnetic flux is equal to BA cosine of theta, and theta is the angle between B and A. B is magnetic flux density, or simply we can say magnetic field density, and A is the area normal vector. Now if you look at the magnetic field inside the solenoid, you can simply see that magnetic field inside solenoid is almost uniform. As you can see here, inside the solenoid, magnetic field is uniform. So the density of magnetic field inside the solenoid is uniform, and the smaller coil is placed inside the larger solenoid. So the B for the smaller solenoid and B for the larger solenoid is the same. So the magnetic flux density for smaller and larger is the same. So simply we can write down in this case flux is equal to BA, because in this case if we take one loop, this is one loop, and magnetic field in this case is passing through this loop. So the angle between B and area normal vector is 0, and cosine of 0 is equal to 1. So simply we can say flux is equal to BA. From here we can say that flux over area normal vector, this is equal to B, but B in this case, this is constant. So simply I can say this is constant. So we can say that magnetic flux for the smaller solenoid divided by area, cross-sectional area of the smaller solenoid, this is equal to the flux of larger solenoid divided by cross-sectional area of larger solenoid. As area of smaller solenoid, this one is small. So if this value is small, so I will say this arrow down means if this value is small, so flux has to be small because the ratio has to remain constant. Now if this area is larger, so this flux has to be larger. So in this case simply we can say as AL, this is greater than AS, so the flux of larger solenoid, this is greater than flux of smaller solenoid. This is what you need to understand. I explained you in detail, so in future you can handle these questions with confidence. Now let's try to write down the answer, and this question has only 1 mark. So here is only 1 mark and this is B mark. So simply you can say flux in larger solenoid is greater, or you can say flux in smaller solenoid is less. So here we have written flux in smaller solenoid is less. If you have written this, you will get 1 mark, and this is B mark. For part B, we need to compare the magnetic flux linkage in the two solenoids. First of all, let's try to understand what is magnetic flux linkage. Magnetic flux linkage is simply equal to N times flux. So this is N times flux. Or simply you can say this is equal to N times BA. Now we need to compare this one. So we can rearrange this one again. So in this case, we can say magnetic flux linkage divided by NA. A is the cross-sectional area and N is the number of turns. This is equal to B, but B for both coils is the same. So we will say this is equal to some constant. So this is constant because B is constant. Now we have to compare magnetic flux linkage divided by number of turns on the smaller coil times cross-sectional area of smaller coil. And this one has to be equal to magnetic flux linkage of the larger coil divided by number of turns on the larger coil times cross-sectional area of the larger coil. So this is simply we need to compare now. But if you look at the smaller coil, so let me rewrite here. So I will rewrite this one. This is the magnetic flux linkage for the smaller coil, and this is divided by number of turns. Number of turns we have 3000 on smaller coil. So number of turns we have here, and the cross-sectional area of smaller solenoid is 1.6 times 10 to negative 3. If we write down for the larger solenoid, we have only 600 turns, and cross-sectional area of larger solenoid, this is 6.4 times 10 to negative 3. Now if you compare these two, means if we compare NS times AS with NL times AL, so this is greater. So if this quantity is greater, it means this one has to be greater, and this one is small, so this one has to be small because the ratio between these two is the same. So here simply we can conclude magnetic flux linkage of smaller solenoid is greater than magnetic flux linkage of larger solenoid, and this is what we need to write down in our answer. So you can multiply, you can find out actually this area is 4 times greater, but number of turns on smaller solenoids are 5 times greater. So it means overall this one is greater. So magnetic flux linkage of smaller solenoid is greater than magnetic flux linkage of larger solenoid. In your answer, simply you can say greater in smaller solenoid. And this is 1 mark. So if you have written this one, you will get 1B mark. For part C1, we need to state Lenz's law of electromagnetic induction. And this question is very common, most frequently asked in many past papers. So you need to understand how to state Lenz's law in a proper way so you can get full marks. For this question, there are 2 marks, and mostly this question has 2 marks. So you need to understand how those 2 marks will be given and what you need to write down in your answer to get those 2 marks. So let me show you how to state this one. In your answer, you have to mention direction of induced EMF, means the polarity of induced EMF. And this has 1 mark, M mark, and this is must mark, mean you have to state in your answer direction of induced EMF. If you didn't write direction of induced EMF in your answer, you will not get this mark, and you will also not get the second mark because the second mark is depending on the first mark. Then you need to say that direction of induced EMF is such as to oppose the change. You have to mention change because this is underlined, so it has to be in your answer. That caused it. You will get the second mark. So this is A mark. Direction of induced EMF such as to produce effects that oppose the change that caused it. If you write down in this way, means in a proper way, you will get these 2 marks. So pay special attention to direction of induced EMF and change because these has to be in your answer. Now let me explain you a little bit about Lenz's law. What exactly Lenz's law is? What does it mean by oppose the change? Imagine that there is a magnetic field. So this is magnetic field that is into the page, and this is uniform magnetic field. And this uniform magnetic field, I will say this is external magnetic field, and direction of this magnetic field is into the page. Now imagine that if this magnetic field is increasing with time. So this is time dependent magnetic field. So this is increasing with time. And now if we place a loop inside this changing magnetic field, if we place loop inside this changing magnetic field, so the magnetic field means the magnetic flux inside this loop will increase. But this loop, they don't like the change in magnetic flux, so they oppose the change. So this is what is meant by oppose the change. Now what is the change here? Magnetic flux is increasing. So this loop will produce current, means current will be induced in this loop, or you can say EMF will be induced. In this case, EMF and current, because this is complete loop. So current will be induced in this loop in such a way that it will produce its own magnetic field that will oppose the change, means that will try to reduce the external magnetic field. Now if external magnetic field is into the page, so the induced magnetic field has to be opposite, means it has to be out of the page. So means it will produce its own magnetic field that will be out of the page. Now if the magnetic field due to current induced in this loop is out of the page, you can find direction of current, means direction of induced current. You can use right hand grip rule and you can find out direction of induced current, means the B. B in this case you have to use, this is out of the page. And then you have to use your right hand grip rule and you can find out direction of induced current. So B is out of the page. So your thumb is pointing out of the page. So you need to curl your fingers. So in this case, this is counterclockwise and this is direction of induced current. So this is I induced and this is counterclockwise, I will say CCW. This is what is Lenz's law. They oppose the change, and change means in this case magnetic flux is changing, is increasing. So loop will oppose that change. So it will try to reduce flux inside itself. So it will produce its own magnetic field in opposite direction. So this is Lenz's law in a nutshell. I hope this point is clear. Let's move on to next one. For our second part, it is given to us the terminals of the smaller solenoid are connected together. It simply means that these terminals are joined together. Now the smaller solenoid is just like a closed loop. So simply we can say it is a closed loop now before it was open loop. The smaller solenoid is removed from inside the larger solenoid. Means we move this one to the left. So we move this one to the left. We need to explain with reference to magnetic fields why a force is needed to remove the smaller solenoid. This question is also based on Lenz's law. So let's try to understand how we can approach this question. Let's try to do another example based on Lenz's law. So we will use one very simple example so you can understand concept of Lenz's law in a proper way, and then we will use that concept to answer this problem. Imagine that we have a uniform magnetic field, and this uniform magnetic field is into the page, and we place a loop of wire. This is a conductor we place inside this uniform magnetic field, and this uniform magnetic field is decreasing with time. So our external magnetic field is into the page, but now in this example it is decreasing with time. So this is time dependent. This is decreasing with time. So when external magnetic field is decreasing with time, it simply means that the magnetic flux inside this loop is also decreasing. But this loop will try to maintain the same magnetic flux. It will oppose the change. So in this case, external magnetic field is decreasing, so it will induce its own magnetic field in the same direction. Means induced magnetic field also will be in the same direction, mean it will be into the page. So external and induced magnetic field, they will be into the page. Current means magnetic field due to induced current in this loop is into the page. So we can find out direction of current by using right hand grip rule again. So you can use right hand grip rule. But in this case, induced magnetic field is into the page. So you can find out direction of induced current. So as induced magnetic field is into the page, so current will flow clockwise in this case. So this is direction of induced current. So this is clockwise. Now, if you look at setup of larger solenoid and smaller solenoid, we can simply understand as we move this smaller solenoid out of the larger solenoid, magnetic flux inside smaller solenoid will change. As magnetic flux inside the smaller solenoid will change, there will be induced EMF. But this is a closed loop, so it means there will be induced current as well. And induced current will produce its own magnetic field to oppose the change in magnetic flux. As magnetic flux is decreasing in this smaller solenoid, so I will write down here the B external inside the smaller solenoid as this one is decreasing. So the B induced and B external, they will be in same direction, and the same point we have already discussed here. So they will be in the same direction. Now we will take the smaller solenoid and larger solenoid. Now imagine that this one is a larger solenoid and this is the magnetic field of larger solenoid. We place our smaller solenoid first of all here. Then we move this one to this point. So you can see magnetic flux is decreasing inside the smaller solenoid. And then let's say we place our smaller solenoid somewhere here. So the magnetic field of this smaller solenoid due to induced current has to be in the same direction. If you look at larger solenoid, it has north pole here. So it means this side of smaller solenoid has to be the north pole and this side has to be the south pole. If I simply draw these magnetic fields due to these two, I can simply say this is larger solenoid. So it has this side is N and this side is S. I will say this is larger solenoid because this picture is not very clear. Maybe it will be a little confusing one. This is magnetic field of larger solenoid. I will say this is N, this is S. And the smaller solenoid. So this one is the smaller solenoid. So this is smaller one. Its magnetic field also has to be in the same direction. Mean this side has to be N, this side has to be S. Now you can see S and N, they will attract each other. So it means there will be attractive force on this smaller solenoid. So we have to apply force to move this coil out of the larger solenoid to overcome the attractive force between larger solenoid and smaller solenoid. That's all what we need to understand. So in this case, first of all, we can say magnetic flux changes inside smaller coil. So we can say magnetic flux changes inside smaller solenoid. When magnetic flux changes inside smaller solenoid, it produces its own I induced. I can say it produces its own I induced. And that I induced will produce its own magnetic field. So we will say that I induced will produce its own magnetic field. And magnetic field of induced current and magnetic field of larger solenoid, they will be in same direction. So they will be in same direction, and there will be attractive force between these two solenoids due to two magnetic fields, due to interaction between two magnetic fields. So that's all what we need to write down, and this question has 3 marks. So let me show you the answer now. This is how you can write down your final answer. Change of flux linkage in the smaller solenoid induces EMF in smaller solenoid. So we can say magnetic flux change, so it means there is EMF induced in smaller solenoid. And smaller solenoid is a closed loop, so there is also induced current in smaller solenoid. And induced current will cause magnetic field around smaller solenoid, and these two fields, they will interact with each other because one N and S, they will attract each other and there will be attractive force. And that's all what you need to write down for this one. This is a typical type of question. You need to understand this concept. In this lesson, we have discussed Lenz's law in detail. So try to understand these concepts and try to handle questions about this topic with confidence. If you have any questions about this one, if any point is not clear, just leave your question in comments. Welcome to A-Level and AP Physics. In today's lesson, we will discuss a typical type of question on rectification from March 2022, Paper 4, Variant 2. In this lesson, we will discuss how to complete full wave rectification circuit, and also we will discuss how to write the equation for sine graph. At the end of the video, we will also discuss how to calculate mean power dissipated in a resistor. For question number 7, part A, it is given to us alternating current is converted into direct current using a full wave rectification circuit. Part of the diagram of the circuit is shown in figure 7.1. For part A, we need to complete the circuit in figure 7.1 by adding components in the gaps, means in these gaps. For the second part on figure 7.1, we have to use plus sign to mark the positive output terminal of the rectifier. This is kind of typical question, and you will see this question in many past papers. So now I will explain you one very important method to handle this type of problems. I will explain this question with the help of answers. So let me show you the answer first, and then I will explain you how you can write down the answer. So this is what question is asking you to complete the diagram. First of all, for part 1, you have to draw these two diodes. This is diode 1, I can say you have to draw here, and this is the second one you have to draw here. And the question was asking you to use the positive sign. So in this case, this is the positive sign. And this one we can say is negative. Positive sign simply tells us means current always will flow. Imagine that this one is a resistor. So simply we can imagine that this is a resistor. So this is DC output. You can imagine there is one resistor. So in this resistor, current will always enter from this side. So that's the reason we mark this side as positive side. Current will enter always from this side. So that's the reason with the help of this circuit, we have converted AC into DC, because in this component current flow only in one direction. So this is how we have converted AC into DC. Now let me explain to you how to complete this diagram. So we will look at these points. So first of all, we will look at point A, and let's say this is point B, and let's say this is point C, and this point is point D. Now, if you look at point A, it is connected with one terminal of the resistor, and B is connected with other terminal. But if you look at these points here, if you look at diodes now, these diodes, they diverge. You see, they are diverging. So these diodes, they diverge. So simply we can say they are diverging at this point, diverge. And where these diodes, they diverge, that is always negative. And if you look at this point, these diodes, they converge to this point. So we can say this point where these diodes converge. And that side is always connected with positive. So this is the point you need to understand. Where these diodes diverge means go away, that is negative terminal of this DC output. And the point where they converge, that is connected with positive terminal of DC output, or you can say resistor. And remaining two terminal you can connect with AC input. So this point, other 2 points, points C and D, they are connected with AC input. And this is true for any shape of bridge rectifier circuit. How they draw, it doesn't matter. If it is a full wave rectifier circuit, you can just follow these points. Where diodes diverge, that has to be negative terminal of DC output. Where they converge, that one has to be positive terminal of DC output. And the remaining 2 points, you can just simply connect with AC input. And this is how you can answer. Let me know if you have any questions about full wave rectifier circuit in comments section. For part B, the output voltage V of an AC power supply varies sinusoidally with time as shown in figure 7.2. So as you can see, simply this is a sinusoidal graph, or this is simply a sine graph. In this case, you can see on y-axis we have voltage and on x-axis we have time. For part 1, question is asking us to determine the equation for V in terms of t, where V is in volts and T is in seconds. So if you look at this graph, this is a sine graph. So we can write down the equation for sine graph. So V as a function of time, this will be equal to V naught, means the maximum value of V, times sine of omega t, sine of omega t. Now we need to plug in values of V naught and omega. First of all, the value of V naught means the V max we can read from here. V max is equal to 3.5. So simply we can write down V naught is equal to 3.5 volts. Now we need to find out value of omega. That omega is equal to 2 pi over t, and t is the time period. Now if you look at this sine graph, this is one complete cycle. So this is one complete cycle. So we can read the time period from here. Time period in this case is equal to 2.5. So we can replace capital T with 2.5. So this is time period 2.5. If we simplify this one, means 2 divided by 2.5, and this is multiplied with pi. So we will get 0.8 pi, and this is value of omega. Now simply we can replace V naught with 3.5 sine of omega t, and omega is equal to 0.8 pi times t, and that's all what we need to write down for this question. And this question has 2 marks. This question has 2 marks, and the first mark you will get if you have got the right value of omega. So this is C mark. And the second mark is A mark. If you have got the right equation, you will get the second mark, and this is A mark. But if you have got the right answer, so still you will get 2 marks, even you haven't written this one, so you will get 2 marks. But if your answer is wrong, you have calculated value of omega right, you will get 1 mark. For the second part, it is given to us that the power supply is connected to 12 ohm resistor, and this is the output of the power supply, and question is asking us to calculate the mean power dissipated in the resistor. So we have to calculate the mean power dissipated, so simply we can say this is P mean. In order to calculate P mean, we have to use RMS value of the V. So we can say V RMS square divided by R. So this is how you can calculate. But Vrms. So let me write down here Vrms. This is equal to peak value of V means V naught, or simply you can say the peak value of V divided by root of 2. Now we can replace Vrms with peak value. So we can say this is the peak value divided by root of 2 and the square of this, and this is divided by r. Now if we simplify this one, we can say this is V peak value of V square divided by 2r, and now we can plug in values of peak value and resistor. So in this case the peak value is 3.5. we have already discussed this is peak value 3.5. Peak value is 3.5 and this is divided by 2 times the resistance of resistor. And now we can simplify and we can get the final answer. In this case the final answer will be 0.51 watts, and this is the final answer. This answer has to be up to 2 SF because this has 2 SF and this also has 2 SF, least number of SF. So this is our final answer for this question. This question has 2 marks. If you have written the right formula, you will get 1 mark, and that is C1 mark. And the second mark is answer mark. If you have got the right answer, you will get the second mark. Welcome to A-Level and AP Physics. In today's lesson, we will discuss a typical type of question on astrophysics from March 2022, paper 4, variant 2. In this lesson, we will discuss how to state luminosity of a star. We will also understand what is flux intensity, radiant flux intensity. Then we will talk about Stephen-Boltzmann law. We will also discuss Wien's displacement law. And also, we will do some calculations based on these 2 main laws. For part A, we need to state what is meant by luminosity of a star. Luminosity of a star is the total energy of radiations emitted by any star per second. Simply, we can say this is the total power of radiations emitted by the star. And luminosity of a star, it is distance independent, means it does not depend on distance from star. This is how you can write down your answer. And this question has only 1 mark. If you have written this mark, you will get 1 mark. Let's move on to part B now. For part B, it is given to us that luminosity of the sun is this, and the distance between sun and our planet is given is equal to 1.51 times 10 to 11 meters. Question is asking us to calculate the radiant flux intensity of the sun at the earth and give a unit with your answer. And so it's very straightforward question. Radiant flux intensity is equal to luminosity divided by 4 pi d squared, and d is the distance from the star. Now simply we need to plug in values and we can find out our answer for flux intensity. In this case, luminosity is given, that is 3.83 times 10 to 26 divided by 4 pi d squared. D is the distance from the sun, or simply you can say from the star. Distance is 1.5 times 10 to 11 squared. And if we solve this one, our final answer in this case will be 1340 watt per meter square. That's all what we have to do for part B. So simply we can write down here, this is the magnitude and the unit is per meter square, watt per meter square. This is the unit of radiant flux intensity. Radiant flux intensity, it depends on distance. If the distance from the star increase, then radiant flux intensity will decrease, and vice versa is also true. If the distance decrease, flux intensity will increase. If we talk about the marks, this question has only 1 mark, so that is B mark. If you have written this one, you will get B mark. And this question has 2 marks, so the first mark you will get if you have written this formula, and the final mark is the answer mark. If you have written the right answer with right unit, you will get the second mark. For part C, question is asking us to use data from B to calculate the mass that is converted into energy every second in the sun. But for luminosity of the sun is given, and the luminosity of the sun is 3.83 times 10 to 26 watts. It simply means that this is equal to 3.83 times 10 to 26 joules per second. Means sun is emitting this amount of energy per second. Now we need to find out the mass converted into energy. So we have to use E is equal to mc square. We have energy, we have to calculate mass. So simply we will say in this case mass is equal to E over c square. But the value of E is given to us, that is 3.83 times 10 to 26 joules per second divided by 3.00 times 10 to 8 square of this. If we solve this one, we will get our final answer 4.26 times 10 to 9 kgs. So this much mass is converted into energy per second in the sun. So this is what question was asking us to calculate. So our final answer is 4.26 times 10 to 9 kgs, kilogram. Our final answer has 3 SF because this quantity has 3 SF. So that's the reason our final answer is up to 3 SF. So you have to use 3 SF in this case. And this question has only 1 mark. If you got the right answer, you will get this mark. For part B, the radius of the sun is given. That is equal to 6.96 times 10 to 8 meters. We need to show that temperature of the surface of the sun is equal to this. So this question is quite straightforward one because luminosity of the sun is already given. So we can use simply Stephen-Boltzmann law. And according to Stephen-Boltzmann law, luminosity is equal to 4 pi r squared times sigma times T to the power of 4, and this is temperature in Kelvin. If we use SI units, our final answer will be in Kelvin. Now we need to calculate temperature from here, so we can write down temperature T. So simply we can write down temperature T in this case will be equal to luminosity over 4 pi r squared times sigma to the power of 1 by 4. And now we can just plug in values. Luminosity was given, that was 3.83 times 10 to 26 watts. We have to divide by 4 pi times r square. Radius is given, that is 6.96 times 10 to 8 square, and sigma is Boltzmann constant. Value of sigma is 5.67 times 10 to negative 8. So this is 10 to negative 8. Now if we solve this one, our final answer for T will be 5770 Kelvin. So temperature is equal to 5770 Kelvin. So this is what we need to show. And this question has only 1 mark. If we got right answer, we will get 1 mark. So this is our answer mark. For part E, it is given to us the lambda max of light for which the maximum rate of emission occurs, means the peak of this curve, the peak. So this is the lambda max. Not means the maximum value of lambda. In fact, this is the lambda at which the maximum rate occurs. So that is called lambda max, not the maximum value of lambda. Means the value of lambda at which maximum rate of emission occurs. That is called lambda max. Lambda max for the sun is given. This is equal to this. And temperature of the surface of the star Sirius is given. That is equal to 9940 Kelvin. But temperature of the surface of the sun we have already calculated in part D. That was equal to 5770 Kelvin. We need to find out lambda max for the star. For Sirius, means for this star we need to find out. We will use Wien's displacement law in this case. According to Wien's displacement law, lambda max T, this is equal to 2.898 times 10 to negative 3 meter Kelvin, not millikelvin. So lambda unit is meter. This is temperature. Temperature unit is Kelvin. So this is meter Kelvin, not millikelvin. Now simply we have to use this. So in this case we can say lambda max T. This is for series. This is equal to constant, and if we use the same for the sun, that also will be equal to lambda max times T. It simply means that product of lambda max T is constant. So we can say for the star we can use 1. So I will use 1 here. For the sun I will use S. So this is TS. Simply I can say this is sun, this is sun. I'm using 1 here for the star. We have to find out lambda max 1. So this is lambda max 1. This is for Sirius. So this is for the star. So we can rearrange. We can say this is lambda max of sun times surface temperature of sun, and we can divide by surface temperature of the star. So I will write down star here, surface temperature of the star. Lambda max for the sun we have, that is equal to 5.00 times 10 to negative 7 meter, and surface temperature of the sun is 5707 Kelvin. We can divide by surface temperature of the star, that is 9940, and we can find our final answer. Our final answer in this case will be 2.90 times 10 to negative 7 meter, and this is our final answer up to 3 SF. This is final answer. Simply you need to understand how to use Wien's displacement law. The product of lambda max and temperature, not time, and temperature is always equal to this one. So that's the reason we have said lambda max times temperature for the star is equal to lambda max times temperature of the sun, surface temperature of the sun. These two, they are equal, and then we can find out lambda max for Sirius. So very straightforward question. If you follow these steps, you will get 2 marks. In this case, 1 mark will be for this law. If you have used this law, this will be C mark, and the final mark will be answer mark if you have got the right answer.